She wasn't able to answer the immigration lady. When's your husband's birthday? August? Of what year? 84? Of what day? Past? Okay, so let's just finish this up. I only got a couple more pieces of paper, pages to go through, and then I'm going to leave you with some exercises. I'd like you to stay today and go through that worksheet. You really need some practice with the sigma notation. It's a new notation, and you need to wrap your head around it. Okay, so what we've been working with all day are called Riemann sums, Riemann being the mathematician who used them first. So we're going to go through, and I'm going to write the left endpoint estimation, right endpoint estimation for the general case. That is just for an arbitrary function f. So this is the case. We have f, which is a real valued function, over. Now I'm going to change the interval to be the arbitrary interval a through b. Right? We have been working from 0 through 1, which is simplified things a touch. So we're now going to generalize it, so we're going to go from A through B with random samples. I may regret of doing this one first because it's actually going to be more complicated than the one that comes afterwards, but okay, well, we'll just deal with it. Okay, so how am I going to write the sum of this so that it gives me the left and right endpoint estimation? So here's the scenario we're in. Right? I'm on the real line. I'm going from A to B. The samples are made randomly. Right? So suppose I have this is x of k, and this is a k plus 1. I need to know what the space here between two sample points are. What is it?
Xk plus 1 minus xk.
Yeah, it's just this minus this. And if I sort of take that distance away, you're left with that. So the delta x here for the kth one, well, it depends on the interval, so maybe I'll remove that. That space in here is just going to be x k plus 1 minus x of k. Our first sample is going to be here. Our last sample is going to be here. And because these are random samples, there is no pattern that governs the sample points. Like I can't write a nice equation. The only way to move from here now is to use a computer. Right? Someone gives you a collection of random samples and you have to run to the computer and get an approximation. Okay, so how do I get let's do the left endpoint approximation first. What are the sample points here? Well, it's just x0, x1, and what's the last sample point I'm going to take?
Xn minus 1.
Yeah, the second last one, xn minus 1. Okay, so I want to go from k equals 0 to n minus 1. Then I need to find delta x. And that's going to be xk plus 1 minus x of k. All right, that's the width of the rectangle. And then I just take the height. So this is the left endpoint estimation with random samples. Okay. The right endpoint estimation with random samples is this guy. Oh, 1 to n of k. X of k minus x of k minus 1 f of x. Okay. Problems?
Just a quick question.
Mm-hmm.
Shouldn't it be k equals a, or?
No. We're not counting from A. Like I'm saying like this sample, then this sample, then this sample.
So
Right? This k is an index for the sample. Right?
Okay.
Well, the first like this x naught Klein is A. Like it does start at A. Right? So don't use the index because like that only worked with our last example because it was a very nice one. We spaced out the things equally. I could predict where the kth sample point was. These samples are random. No one can predict where they are. You can give me a probability density function telling me where you expect them to be, but you're never going to get a pattern out of this. Anyways, this one's not too important. Right? This one's just the standard. I'm just giving you the definitions of the Riemann sum for random samples. That's really it. Right? What's more interesting will be coming up with this same sort of, same guys, but with equally spaced. Right? So let's do case, basically the same case with equally spaced samples. Okay, so I guess this is the one to understand, if you want to understand. This will be more useful when we return to probability. Okay, so how do I divide the region here from A to B into n many pieces that are equally spaced? Okay, so here's the first point, x naught. That's the first sample point. If I break the interval A through B into n many pieces, what is the space between 2 points? Exactly. The distance from here to here is b minus a. Agree? So we just take b minus a, that distance, and divide it by n, the amount of intervals we want. So delta x for these equally spaced intervals is b minus a over n. Okay, so that's going to be here. So this next one here is going to be, so what's this point here?
Plus A.
Plus a?
Like the b minus a divided by n plus a.
Well, let's think about this. I know this point is a. I know that this next point is delta x away from it.
So delta x plus a.
Yes? Let's go more. So what's this point?
Is it A plus 2 delta?
A plus 2 delta x. Okay, so I can get a pattern here. So the kth one is going to be A plus k many delta x steps down the road. Savvy? Okay. So I got my sample points. So my sample points, generally speaking, are these. A plus k delta x for k from 0 to, what's the last k? N. N many steps down get us to B. Let's confirm this, right? So I'm saying that if I put n into here, we're going to get B. Eh? So A plus n many steps of B minus A over n. That will cancel. You get A minus A plus B. Lo and behold, we've made it to B. Okay, so here's the sample points, here's the width. So very easily, the right endpoint estimation is going to be sum from k equal right endpoint 1 to n. And I'm going to write it like this. F of the kth sample delta x. Okay, so I could really write this like this. To n of A plus delta x B minus A over n. Okay. So you can just give this to a computer and go off to the races. But generally speaking, the first thing we did in class was just set up this equation. I'm just now doing it with an arbitrary f. I just used an example so we could work with something real. The left endpoint estimation is just the same thing, but we're working from the left endpoints. All right. So can you see this now as being the area under the curve when you look at this, right? Because that's how I set it up. Right? This is going to add together n many rectangles. Savvy? So this is the area under the curve between A and B. Okay. Remarkably similar, don't you say? This is just notation for this when we take n to infinity. Sum these heights and take x's, infinitely many of them, between A and B. And this is notation for saying take an infinite number of samples between the interval A and B, and then multiply by the width, which in this case is going to be pointwise width, times the height. That's what this symbol is.
So that's an infinity, right?
Yeah. It's not derivative. This is never derivative. This was always tiny interval, right? Pointwise interval. This means tiny distance. This means not tiny. And if we take a limit into this, that's why we go from here to here. Right? Big difference, tiny difference. It's so tiny actually that it's infinitesimally tiny. Right? Sample point. Yeah. So now the samples are in place. Since we're taking an infinite number of samples, we no longer need a name for them. Because you need to do it at every point in between A and B. And that's how you interpret this, right? Summing up an infinite amount of rectangles of infinitely small width at every position between A and B. Which actually just works out to this. Right, so that's why I went through so much effort today setting up the geometry. Because this is the last thing. Okay. Now, to go from here to here, for f, the antiderivative of f, as you all probably know, and some of you may have been told this by your teachers, this is a huge step, right? You should not believe me when I say this. This is such a remarkable, almost unbelievable assertion that all of this work that we did today can actually just be done if you find the antiderivative. Why should the antiderivative have anything to do with area under the curve? Right, so for this equality, we need the fundamental theorem of calculus. That's why it's important. Yeah.
So this fundamental theorem of calculus is like where we're going to kind of put everything like summation, area, and the antiderivative together.
We're going to take the geometry of the area and associate it with the algebra. The same way we did. Do you remember when we had like the limit definition of derivatives?
Yeah.
And then I showed you that we could actually do it algebraically and it gives us the same thing?
Right.
That this is what this is. Same thing. I'm saying we can do integration from first principles every time. It is cumbersome and usually impossible. So it turns out that there's an algebraic way of doing it, which is more amenable to which are more solvable, let's say, and faster.
Okay, so right. Like next class you show us like.
Next class, Mike is going to show you.
Okay, so
why, how it is possible that this quantity is giving you the area under the curve, which is something that everyone has taken for granted, which is.
So sorry. We would use the antiderivative to solve for the area under the curve.
Yeah, but why? Why is that giving you why does it give you the area under the curve? You were just told that it gives you the area under the curve. I computed the area under the curve from first principles, right? By taking rectangles. What I have done today is very much definitely computing the area under the curve. The assertion that this is going to give you the same value. It's amazing that that happened. Why should taking an antiderivative have any relationship with the area under the curve? This is something that's going to have to be established by us.
Okay, so that's like a shortcut. So like.
Shortcut. Oh, this will be, well, yeah. The same way that like taking derivatives algebraically is a shortcut over the first principles method.
So would
Yeah.
we be required to do both?
I'm going to ask you to take a Riemann approximation of an integral, for sure. I will say something like, use 6 rectangles and give me an upper and lower approximation to this integral.
Okay.
Yeah.
Would you ever ask to have like infinite amount?
No, it's too hard.
Wait,
Yeah.
so like you're taking the antiderivative of A and B, right?
I'm taking the antiderivative of f. Like the antiderivative has this property, remember? F prime is equal to f. This is my final thought. I haven't established any of this. This is going to require an entire lecture, right?
So if the
Yeah.
And you're given some kind of interval between A and B.
Well, that's what we're saying, right? Like I'm saying, what is the integral from 0 to 1 of 1 minus x squared dx? We don't know this yet, technically, but you can actually take the antiderivative of this already, right? This is going to be x minus x cubed third from 0 to 1, which gives you 1 minus a third minus 0 minus 0, which is 2/3. Okay, so I can do it immediately rather than spending a whole lecture doing it from first principles. But hold on. This is an incredible claim. Why is this giving us the area under this? Is why? It's just the antiderivative. What the hell does that have to do with anything? Yeah. Shh. Huh?
The 0 to 1, doesn't that mean we would add them, the sum?
No, it's the difference.
So then,
Again, this is all from the future. I can't explain any of this because I haven't even shown it to you yet. Right? So don't stress yet. But it's definitely top minus bottom. Right? That's the rule is this. Minus. Okay? Okay. Do your worksheet, please. Okay. I'll write some extra questions on the board.